Hey everybody, this is AHaH Computing in a nutshell. I'm your guide, Alex Nugent, and this episode is about the adaptive power problem. In a previous episode, we concluded with a slide like this, which showed that the difference in operating voltage between our modern computers and your brain, my brain, the neurons in our brains, is a factor of about 18. And that the amount of energy that we dissipate goes as the voltage squared. And so if we can reduce the voltage by something along the lines of 18 times, the total amount of energy that we're going to reduce is going to be in the hundreds. And the question is, well, what's the catch? Because you clearly, there's something has to be going on there, because why don't we just lower the operating voltage of all our electronics down to, 65 millivolts? And there's a few reasons for that, but there's a very big reason, which is that noise is everywhere. It's something that we like to sort of slip under the rug, kind of idealize, out of our concept of how things work. But really, the technology that we utilize today, the reason it works is because it deals with noise. And digital electronics is actually, it deals with noise in a fairly straightforward way. Okay, so we have these signals which represent state in our computers. And superimposed on these signals is all of this source of noise. Now there's bottom-up noise, thermal noise, sort of inherent in the jiggling of electrons, but there's also other forms of noise. There's wires can act as antennas, and so some other wire can create an electric field when it's charged, and that can induce another electric field over here. And so there's sort of intrinsic, sort of heat-based mechanisms for noise, and there's also this sort of more external, sort of like corrupting signals, sources of noise. But anyway, there's the signal that we're interested in, and then there's all this other stuff that's sort of piled on top. And what we have to do is discretize that signal and buffer it enough so that we can add what's called a noise margin to it. Okay, so in this signal here, right, we have these two states, and if we separate them enough, right, in this case, let's imagine that that's voltage, so that the margin exceeds the noise, then we can clearly differentiate between different states, right? So this blue signal would be the raw underlying signal with noise, and then this red signal here would be our digital signal. We're just taking that continuously variable signal that has all this noise injected, and we're just saying, no, we're going to put a threshold here. If it's above this, it's a 1. If it's below this, it's a 0. Okay, so we add a noise margin. Now, as that noise margin gets smaller, the spurious noise fluctuations will trip over the threshold, and it'll start corrupting our signal. So in this case, we see this, the red digital signal is starting to get corrupted by the noise as our noise margin approaches the magnitude of the noise. Right? So it's fairly simple to understand, and it's sort of like this guy here. He didn't build up enough margin, and the real world is filled with all of these bumps and potholes and whatnot. And so if you don't build in enough margin, your machine just doesn't work, right? It stops working. And this is a really big reason for digital electronics. There's all this nastiness that's going on, and by making digital signals and by making our voltages a little bigger, we can kind of wash over all of that. We can sort of create a margin and work within that margin. Okay, now modern machines are really this like top-down mindset. We take the thing that we want to build, we decompose it into all of its bits and pieces and parts, and then we assemble the parts together in order to form the whole, and the whole is the sum of the parts. And modern integrated electronics is just a really extreme manifestation of this, and it's just all of these very, very precisely arrayed transistors and wires all stacked up in multiple layers. Every piece in its specific place doing its specific job, literally, built out of a crystal. This is how we build machines, and whenever you inject noise into the system, if the noise is too high, then it just stops working, right? So, and the noise can come from the underlying signals that it's processing, but it can be inherent in the material itself. It could be defects in the manufacturing process, or a wire could break, or short, or something. Things can happen in various ways that are not ideal, right? We don't just design this nice, perfect, everything in its proper place system. Modern integrated chips are very close to that, but there's this imperfection that occurs both in the fabrication but also in how we use it. And whenever you inject noise into that, things can run amok very quickly. So you have to design with that in mind. Okay, so let's take a brief aside and talk about memristors, or memory. So you can think of a memristor as a collection of what we call metastable switches. Okay, now each one of these switches has two states, right? Well, so this would be the A state, the B state, and they differ in their resistance. And they're separated by this potential energy barrier, which you can see right here. And that barrier doesn't have to be equal in the sense that it might take a lot of energy to go from state A to B, and less energy to go from B to A. But regardless, there's this barrier potential. There's this potential energy that has to be overcome in order to have a transition. And we see this reflective in the hysteresis loop of a memristor. So if you look here, let's look at the blue curve. As we increase the voltage, it starts off as sort of a low conductance device, and then we hit this forward adaptation threshold, and it causes the conductance to increase. And so the slope of this line increases, and we bring the voltage back down, and it's stuck in that state until we hit the reverse adaptation threshold. And it falls back into a low conductive state. Okay, so the potential from going from one state to another is it's asymmetric. It doesn't have to be asymmetric. It just depends on the specific physics of the device. But the key here is that these thresholds exist. And in order to induce a change in the memristor, you have to raise that voltage up to whatever that threshold is. Okay, so now this is where it gets interesting. If we want to change the memristor, and thus enable learning or programming. Okay, remember, we're really after building learning systems. We also want to be able to program, but I'm more interested in learning. So in order to do that, we have to change the resistance of the memristor. But in order to do that, our voltage has to exceed the adaptation threshold, right? So if we wanted to make the device more conductive, we have to apply voltage that exceeds this adaptation threshold. But wait a minute, if we want to create very power efficient systems, we want to lower the voltage a lot. But we also want to have the ability to change, which means we have to lower those barriers. But as we lower the barriers, we start to hit up against noise intrinsic in the system. Our noise margin, this is literally our noise margin for adaptation, that becomes smaller and smaller and smaller and smaller. So intrinsic fluctuations in the system, heat can give rise to voltage fluctuations. That's called Johnson-Nyquist noise. Stray signals in the system. Spurious voltages can cause state transitions in the memristor. And so this is kind of a dilemma, right? In order to create a very low power system, memoristic system, really anything, that also has the ability to adapt, which means to change, then we're going to end up with parts that are constantly breaking, all right? So just think about that. That's kind of a bugger, right? And if parts are constantly breaking, then we need a mechanism to repair the parts that are breaking. Okay, so this is the adaptive power problem, and it's kind of a bugger, right? So we stated what we want. We want low power, and we want the ability to adapt with that low power. But in order to satisfy those two constraints, we have to lower the voltage, and we have to lower the thresholds of adaptation for the memristor. That causes the noise margin to decrease, which leads to decay and volatility. And basically the memristors changing without us changing them. So the parts are starting to break, and we need to fix them. All right, so we need a mechanism of repair. How do we do that? Well, the first thing that comes to mind is what about a fixer circuit? I mean, think about, you're living in your home and your home breaks, you go out and you repair it. So why can't we just take these parts that are breaking and just add this extrinsic repair mechanism, some fixer circuit? All right. Does that work? Well, not really. And there's two reasons for that. The first is who fixes the fixer? All right. If our fixer is composed of the same circuitry and devices and whatnot that our parts are composed of and operates at the same voltage levels, it's very likely that our fixer could just be breaking, and then we have to fix the fixer. Okay, that's a problem. But one could say, well, wait a minute, Alex. No, we'll hardwire this fixer, and we, I could imagine something like that taking place. As a matter of fact, it does. I mean, modern volatile memory technologies have, in effect, a fixer that's constantly repairing the state of devices. The problem here is that more communication is required, right? So if the fixer breaks and you have to fix it, then that doesn't work. But if the fixer doesn't break, you make that non-volatile. But now you're having to communicate information constantly back and forth, right? Because the fixer needs to know what the parts are, what the state is, and so it has to read the state, and then it has to figure out how to repair it. So you end up with lots of communication introduced, which is it's kind of frustrating, right? So repairing the parts with some extrinsic fixer mechanism, if you want to lower the power down to biological level, I mean, really get this thing low, this doesn't work. You try to solve the problem and you'll get you'll get stopped. This is really frustrating, and this is the adaptive power problem. If you want low power and you want adaptation, then your parts are going to be breaking all the time. You're going to be your system is going to be composed of unreliable components. Okay, and this is important to us at Knowm because we're interested in building intelligent machines, very efficient intelligent machines. And intelligence, for all practical purposes, is learning, right? It's just constantly learning, and learning is adaptation. All right, so if we want to create very intelligent systems which learn, which adapt all the time, then we're going to have to solve the adaptive power problem. All right, so that's it in a nutshell, and in the next lecture I will discuss the adaptive power solution.